Good afternoon. Welcome to this EMS webinar titled Build and Simulate Interesting Devices Using Magnet Arrays. My name is Arvind Krishnan and I'm an application specialist here at EMWorks. Today we will be looking at how EMS and SolidWorks can help you guys build better devices using magnet arrays. For the benefit of people who registered but were not able to attend this webinar, we will be recording this webinar, and once the webinar is completed, we will send you a link to access the recording. So let us start with the agenda for today. We'll give a quick introduction to EMWorks, the company. And then we'll start with the topic, which is magnet arrays. What are the applications? What is the EMS approach to solving problems with magnets and magnet arrays? We will also go over some live examples and then finally open the floor to question and answers. During the presentation, at any time, if you have any questions, feel free to use the chat window that is there in the GoToMeeting console. So you can type in your message, your questions at any time during the presentation, and towards the end of this presentation I will actually review the questions and answer them. Now let me start quickly by the introduction to our company and its products. So who is EMWorks? EMWorks is one of the first companies to offer CAD embedded simulation for electromagnetic, electrothermal motion type of applications. We have two products which are completely embedded inside the popular CAD packages of today, SolidWorks, Inventor and SpaceClimb. However, the topic for today is going to be EMS and SolidWorks. The two products are EMS, which is used for electrothermomechanical application, and EMWorks, which is used for RF and microwave application. Now the EMS products, they cover a wide range of applications, and it's probably a very nice way of looking at the applications categorized according to the frequency of the excitation. So EMS, which you see in the left, mainly supports frequencies from DC all the way to a few hundred megahertz, and it covers a lot of electrical machine and electrical applications like motors, generators, solenoids, relays, magnetic levitation, loudspeakers, permanent magnets, coils, sensors, high power bus bars applications, etc. Okay? And towards the right we have what is typically in the high frequency from a few hundred megahertz all the way to a few tens of gigahertz, and that's basically the RF and microwave application, and in that space it's the EMWorks products that caters to those kinds of applications. That's not the topic for today, but nevertheless we offer both these products which are integrated inside CAD. Now let us start with what a magnet array is. As the name suggests, a magnet array is nothing but a combination of permanent magnets. Okay, they're arranged in a very particular fashion, and they are done so to actually produce a magnetic field that actually cannot be produced by any one particular magnet, or either it's a permanent magnet or an electromagnet. So the magnet array achieves a magnetic field which is almost impossible to produce using a single magnet. Okay? Now you see some images of commonly used magnet arrays, and we will today in this webinar look at how we can design these magnet arrays inside SolidWorks and how we can study the magnetic field distribution, the forces on ferromagnetic substances due to these magnet arrays. Now there are many applications for magnet arrays. The one that is very common and well known is the magnets that we stick in our refrigerators. basically the refrigerator magnets. You notice that they stick in one direction on one side, but if you turn to the other side, they don't stick. I mean, and today's webinar might help us understand why that is so and why the use of magnet arrays. And obviously there are some industrial examples as well. Brushless motors are made up of magnet arrays, which help them to spin. Then there is also magnet arrays are typically used in particle acceleration, in laser, generating lasers, in producing free electrons, etc. They are by far the main driver behind maglev trains. And finally, they are also used in voice coils, speakers, etc. And there are numerous more applications in magnet arrays. These are some of the more common ones that I've brought out together. Now let us look at how EMS approaches solving problems using magnet arrays. So in EMS, the first step is always designing the geometry, and that is done using CAD package. In this case, we will use SolidWorks. So we design the model, our concept of the model using CAD, using SolidWorks CAD. Once that is done, then we come to the simulation side of it, which is completely embedded inside SolidWorks, and there we give the program the properties of the magnet. So we assign materials to the different magnets. If there are other ferromagnetic substances, etc., present in this geometry, we also assign materials for those. And also we assign the magnetic directions inside SolidWorks. Now once that is done, we solve for the fields, and then you can compare if the field looks like what you desired. If not, you can go ahead and change the geometry. When I mean the look of the field, I mean the distribution as well as the strength. Okay? And so the 3D visualization tools inside EMS will allow you to understand both the strength of the field and as well as the distribution of the field. And hence you can make intelligent choices about the sizing your models, making it smaller or bigger based on the strength of the field, and also maybe orienting the magnets in a different way to produce the desired field. Okay. So you can make those desired changes as required, and then you can go back and re-simulate the problem to understand how the design changes has affected your strength as well as the distribution. So you can do this iteration inside your CAD package as many times as you want till you arrive at the final geometry or the final design that you desire. And the same steps I've articulated in the form of a flow chart, as you see here. So it's basically the steps that I outlined here are also available in this flow chart. Now this is EMS approach to solving problems using magnet arrays. So now I think it's time for us to take a look at some live examples as to how you can assign magnet arrays, you can simulate them, and you can understand how they look. So without further ado, I'm going to go ahead and open SolidWorks to go over our two examples. Now this is the first example. As you see here, what I have here is an array of cubical magnets. These are just cubes, each one of them, and then they are magnets. So let me go ahead and turn off a few components just to explain the problem better. So these are magnets. They are 2 centimeter cubes. They are placed next to each other, and they form 10 such magnets are placed next to each other, and they form what is called as a magnet array. Okay. What I also have here are 2 blocks of mild steel slightly above and below this magnet array. Okay. Now the objective is to understand, first of all, I've got a distribution of the magnets, the orientation of the magnets have to be understood. So we need to see how the magnets are oriented. And the second thing is to understand what type of fields do they produce. say at the top of the magnet and in the bottom of the magnet, both the distribution as well as strength. And that can be easily measured by having two mild steel components, as you see here on the top and bottom, just to understand, where the fields are high, where it is low, and if it is doing what it is desired. So the first step in doing a simulation inside EMS is to create a study, and that can be done simply by selecting the type of study that we wish to create. Inside EMS, we have several different types of simulation. For simulating magnet arrays, the study type or the analysis type that we use is called magnetostatic. Okay. In magnetostatic, as the name suggests, you can have only DC voltages, DC currents, or you can have permanent magnets. There is no sort of AC, other types of currents are not possible. So in this particular example, there are no currents, so all we have is just permanent magnets, so the most suitable type of simulation will be magnetostatic. One thing that to note here is EMS can couple your simulations, can do multiphysics type of simulations. You can couple your simulation to motion, you can couple your simulation to thermal, and you can couple your simulation to structural. Okay. In this particular example, we will not deal with coupling, and that can be a subject by itself on a different webinar. Now, once you create your simulation, it creates what is known as a study, as you see here. Now, once a study is created, the next thing that we need to do is take a look at some of the components, how to define materials. Now, the first step is to understand that these magnets, the 10 of them, they are all permanent magnets. So we define a material, say neodymium, and material definition is extremely simple in EMS. You apply material. Here we have EMS materials, and you can even see that we have a database that is that comes with a few permanent magnets. For example, a few neodymium magnets are there. Their values, both their permeability and as well as their magnetization, coercivity, and remnants are all there. Now, this is a fully customizable material database, meaning that you can create your own magnets and you can use them for simulation. So in this examples, I've used N42 as the magnet for all my cubical magnets. Okay. Now comes the next and the most interesting part in the simulation is to define the direction of magnets. You can already see that it's been shown here with arrows. So let's just take the first magnet. We need to make sure that it points up in the Y direction. So it can be done by just applying what is known as a coercivity direction to the component, and then we select the Y direction, and here the arrow kind of tells us how the magnet orientation is going to be. Now similarly, we do that for the other magnets as well. The second one, for example, is going to be pointing towards the X direction, which means the north is going to be along the positive X towards the right side of the magnet, and the south is going to be on the left side. Okay. And here you see different arrows. I'm just zooming in. So you can see that one thing is pointing up, the other one is pointing to the right, it's pointing to the down, and then right, and so on, to the left, up, and so on. So each of these directions are marked and assigned using EMS. So let me just maybe make them bigger so it can be visualized better. Okay. So now, depending on how you desire to have your magnet arrays and the orientation, you can do that effortlessly using EMS. Okay. Now, once you do that, then all we are left to do is to define components for other bodies. Here you see these two are mild steel, so I apply mild steel. And the objective of this simulation is to find out what is the force acting on the one that is the mild steel sitting on the top and the one that is sitting on the bottom. With this kind of magnet arrays, you know, they are designed for a particular type of magnetic field. Usually the magnetic field in the bottom is going to be the one that is that's the dominant one, and you should see pretty much hardly any magnetic field in the top. So if our prediction is correct, we need to have a decent force of attraction in the bottom mild steel and hardly any attractive forces in the top. Okay. There is only last thing to do is the concept of air. Now the concept of air is kind of interesting, and that's because the magnetic field, they are present everywhere surrounding the magnet, which is basically in the air or the vacuum that is around it. Okay, so that needs to be modeled as a geometry inside SolidWorks or any CAD system you may use. And as you see here, you need to model the air, and you can apply the property air to this particular geometry. Now once that is done, we need to tell the program to compute the force on the top and the bottom geometry, and that is done using this force dialog box. After it is done, now let's take a look at some of the results. I had run this simulation prior to this presentation, so we'll jump right into the results. Okay. Now this is a finite element based program, so just one thing that I do want to let you know is the concept of mesh. So this program particularly has an automatic mesh creation process. EMS automatically creates the mesh on the components that you have in your simulation, and you have powerful mesh tools which allow you to vary the size of your mesh on each component, on each faces, etc. But by default the program automatically creates an optimum mesh to ensure correct results. Okay. Now with this, let's move on and take a look at the results. Okay, as far as the results are concerned, some of the things that is of interest to us would be, as I said, the forces acting on the top and bottom. So let's go ahead and look at the forces, and they are neatly laid out to us in what is called as a result table. As you see here, the force in the y direction is the major component of interest, and in the top, this is the virtual work 1, which refers to the top magnet, the top mild steel bar. That's very negligible, about 1 Newton in the minus y direction, which tells you that it's going to attract. Okay, but take a look at the force in the bottom one. That's close to about 50 Newton, so it's 50 times more in the bottom. Although the top and bottom are equidistantly placed from the top and bottom surfaces or the middle axis of these magnet arrays, you can see the difference in forces, and that can be explained in a minute when you take a look at the magnetic flux density distribution. So let's go ahead and do that. We can take a look in EMS. You can take a look at magnetic flux density, the field intensity, etc. In the 3D space. Okay. Now this is the section plot of the magnetic flux density, and as you can see here, the magnetic flux density is very high and highly prevalent in the bottom of this magnet array, and hardly existing in the top of it, and that explains the differences in the forces between the top and bottom. Okay. So this magnet array is actually designed to have very high force of attraction in the bottom and hardly any in the top, and that can be explained by the values of the flux density and the you see the distribution here as a 3D plot. In addition to the flux density, one can also take a look at the magnetic field intensities, and let's go ahead and take a look at them. Now I can go ahead and do a section plot of the magnetic field intensity. Now, field intensity is mainly in the gaps between the magnet and the steel bars, the mild steel bars, and that you can see here as you see. So one can take a look at the flux density, the field intensity, and also the results as the forces. So this is one example. Let me go ahead and do walk you through another example that deals with cylindrical magnets. Now we understand that your rectangular magnets are not really the only form of magnets, especially for people in the motor industry and others. They have a lot of cylindrical magnets with various direction for their magnetization direction, and one need to be able to compute the complex magnetic field that results from this. So this is an example. Let me go ahead and hide the air. This is an example where I have many cylindrical magnets, okay, as you see here. And very similar to the previous one. The only difference is you can now, if I just quickly place it here, help you to visualize the directions each of these magnets are going. So what we did in essence is created local coordinate systems for each of the magnets, and EMS allows you to, for example, pick a particular magnet and select the direction based on a local coordinate system. So I can go ahead and look at the coercivity direction, and I can apply the coercivity direction based on how it is oriented. Now in this case it is oriented along the y-axis, and hence it's there. So if you pick another magnet here in this case, you can actually see that the coercivity direction is with respect to a local coordinate system of that magnet, and directing it this way. So now this is pretty much the new arrangement of these magnets that we need to study to see what kind of field they produce. Okay. Just like before, we created a study, we defined the materials of each of the magnets, and what we also have is the air region around the magnets, and also obviously inside this, and we request the program to mesh this geometry and give us the field. So let's take a look at a few of these. Let's take a look at the magnetic flux density as a section plot. So now this is the magnetic flux density just on the magnets, but what we are of interest, thing that is of interest to us is the air as well. So let's go ahead, turn on the air and look at the magnetic flux density through a section cutting the middle of this magnet. So now this is a very, very interesting pattern. You see here is these flux lines. There is hardly any flux towards the center. So if you keep any kind of ferromagnetic substance here in the center, it experiences hardly any force. Okay, and similarly outside. So it's highly concentrated. The flux is highly concentrated around the magnetic region. Okay, and for certain applications that's required, and this type of arrangement helps you to get this flux, and EMS readily helps you to understand and evaluate what these values are and so on. For example, one of a very useful feature in EMS is called the probe feature, and the probe helps you to just identify regions in your model and see what values of magnetic flux density they produce. So for example, I can go ahead and click anywhere in my geometry, and I will be able to get these values. Not only that, these values can be saved out as an Excel or a MATLAB format, as a text format. You can take it into other products as well. Okay. So this gives us the radial distribution of the magnetic flux density. So as before, you can also visualize these, more as vectors. So we're going to take a look at the magnetic flux density distribution due to these arrangement of magnets as vectors. As you see here, there are three lobes, dominating these the three vectors that are here out of these 12 magnets, and then there will be 3 in the bottom. So pretty much this this arrangement of vectors help us understand how the field is highly concentrated in and around the magnets. Okay. It's highly concentrated in and around the magnets, pretty much producing hardly any field towards the center and all through the outside. So if you have some kind of a rotating device on which you're going to stick these cylindrical magnets, and this can actually help you produce the desired torque and maybe help it to rotate, as in the case of a motor or other components. Okay. So these are pretty much the two examples that kind of tell you how one can design these magnet arrays inside SolidWorks, how one can define the direction of coercivity, and take a look at some of the results inside EMS. With this, let me jump back to our presentation, and let me take you over to through the last few slides. Let me talk about the products and bundles that we offer in EMS. Now, EMS, the product that you saw, which I showed you right now, is towards the left, as you see in this particular slide. It is categorized into two separate bundles. One is EMS Professional, that comes with the 6 solvers that you see here. And just to recap, we did just magnetostatic simulations in this particular demonstration I showed you. EMS Premium, on the other hand, has everything that is in EMS Professional. It also has several add-ons that enable you to do multiphysics type of simulation. You can do thermal analysis, motion, structural, as well as parameterization. Now, parameterization is a very interesting feature inside EMS, where you can tie the geometry parameters in SolidWorks like dimensions, etc., and now you can simulate over a range of those values to see how it behaves. For example, if you're not certain about what are the sizes of these magnets, you can actually tie the dimension in SolidWorks as a parameter, and you can use it to iterate and understand how the dimension varies, how the variation of dimension varies the field, the strength of the field, as well as distribution. So parameterization is there as a part of EMS Premium. Now, to EMS Professional, you can add on any of these multiphysics, thermal, motion, etc. All EMS licenses are by default in the activation type license, where you can just activate through the internet. But if you need a network license, we also offer that for an additional fee. As far as HFWorks, this product is concerned, there's just one product, and it has 3 different solvers, as you see. Now, just to recap, to be able to design and simulate magnet arrays that I showed you, what do you need? You need, in this case, SolidWorks Basic, or if you have EMS Inventor or SpaceClaim, any of these would work fine. And then you would need EMS Professional as the product. Now, thank you for watching this webinar. We're just very happy to announce to you that we have over 400 customers worldwide using EMS, and here are some of the names. And how do I access more information about our products? Please visit our website, EMWorks.com. We have white papers, we have customer testimonials, we have a plethora of examples that showcase our product, and then the other resource that I would go in is our YouTube channel, where we have over 50 videos that tell you step by step how EMS tackles several different application areas. Okay. For sales, obviously you can contact your local SolidWorks reseller if you're a SolidWorks customer. Otherwise, you can contact both Adam as well as Jonas. Any of these gentlemen will be happy to help you with the sales questions. So with this, pretty much now we would take a look at some of the questions you asked, and I will be answering them to you. Okay, one of the questions asked is, can you visualize the field lines around the bag magnets to see how the field lines flow out? Yes, absolutely, you can do that. I guess I did not show you the field lines in particular. So yeah, it is possible to do that, and now I'll take this occasion to show you that. Okay. Now we have this particular this one. So we can actually, to any plot, we can overlay that with field lines. So now this will be helpful for you to visualize how the field lines also go out in addition to just a 3D plot. So you can see here the field lines can be plotted in addition to the 3D plot. Okay, you can superimpose one on the other. So if you have a simple bar magnet, yes, the field lines will go from north to south, and obviously you will be able to see that. But even in a complicated arrangement of magnets, as you see here, we will be able to predict the field lines. You'll be able to visualize them. Now another question is, will EMS be able to handle moving objects like motion? Yeah, the answer is yes. You will be able to handle EMS with motion. You need to have this motion add-in that I talked about. With that, for example, if you have a bunch of a magnet array accelerating, and you would like to understand, the forces acting on, say, ferromagnetic substances, etc., or you have some kind of a braking system or a clutch system that has a combination of magnets as well as coils, you will be able to study all of them. So you can have motion coupled to this magnetic simulation. It is possible. The next question is something related to our material database and this one. So just to reiterate, our material database contains commonly used materials in the field of electrical engineering. They are steels, magnets, cables, conductor materials, etc. Obviously, it is not the most comprehensive repository, so we allow you the ability to create your own materials and use that for simulation. So we have almost a lot of standard materials, but we also understand that not every material that's out there in the industry is inside our database, although we are working with a few material suppliers to enable that, and we are doing that with every release. But the good feature of our material database is that you can create your own materials and you can use that for simulation. Okay, there's another question which talks about, is it possible to apply a coordinate system that is other than Cartesian? Yes, the answer is yes, and I would like to just get back to the other cylindrical scenario here. So if you look at our coercivity dialog box, you can apply both global as well as local coordinate system. On addition to it, each of it, you can have cylindrical, spherical, as well as Cartesian coordinates. So to define a magnet, pretty much every possible way one can fathom, we have incorporated that into the program. So it is possible to apply local coordinate system, it is possible to apply cylindrical coordinate system, it's possible to apply Cartesian coordinate system, and so on. Now there's a question on learning resources. What are the learning resources that are available with the program for someone who is new to EMWorks and would like to learn? So first of all, I want to just bring your attention to the EMS tutorials and demo viewer. Now demo viewer is an interesting application inside EMS. Now this demo viewer contains many real-life examples. I would say, like, this is a getting started lesson, so if you are new, this is where you would start. It talks about, it has also a step-by-step instruction along with videos to help you get started. We have a lot of applications which are arranged based on the application. So we have bus bars, we have circuit boards, we have clutches and brakes, and a lot of them have a step-by-step introduction. We also have a whole tutorial series that covers a lot of interesting examples that you can solve and you can learn how to do step-by-step. As we speak, we add more and more examples to the demo viewer that can be updated over the internet, and this is a very valuable resource for you to have as far as learning the product is concerned. In addition to that, we also have help topics, YouTube videos, and these kind of webinar series that can also help to educate users about our product. Okay, there is another question which talks about the tiny details, electrical steel plates in detail. Okay, I think this one refers to the core. What happen? Can you have laminations in the core? I think that's probably the question. Yes, EMS can handle laminations in your steels. So if you have tiny steel plates that are separated by a distance or sandwiched between insulators, you don't have to model each of these steel plates explicitly. So you can have the core as an entire volume, and then you can EMS material allows you to specify laminations and so on. So it is possible to do that here, and I think we have a couple of YouTube videos of maybe some real-life transformer or motor examples which talk about how laminations can be applied in EMS. So with that, I think almost all the questions have been answered. So if there are any more, I encourage you to type it in. If not, I would like on behalf of EMWorks to thank each one of you for attending today's webinar, and I hope it was informative. And if you have any questions, any further questions, these will be your coordinates. EMWorks.com, our website has comprehensive details about how to contact us, YouTube videos, etc. And also we have a couple of email addresses of our sales who will be happy to get in touch with you. Also, if you go to our website and if you would like to try out our program, there is a link where you can request a trial license of EMS. We'll be very happy to send that to you, and you can try EMS for yourself, especially the demo viewer examples, and you can see how EMS can help you, with your electrical and magnetic type of problems that you may have. With this, I would like to end this webinar, and thank you all for your time today. Just a reminder, we will be sending you the recording of this maybe in a day or two. We urge, feel free to share it with your colleagues who couldn't make it today, or with other people whom you think this webinar is going to benefit. Okay. With that, we end this presentation. Have a nice evening, and see you next time. Bye-bye.